Quantum physics is the branch of science that explores how reality behaves at the smallest possible scales, far beyond what human senses can perceive directly, and it fundamentally changes our understanding of existence itself. In the classical world, the world of everyday experience, objects behave in predictable ways, a ball follows a clear path when thrown, planets orbit stars in smooth trajectories, and causes lead to effects in a deterministic manner. However, when scientists began investigating matter and energy at the scale of atoms and subatomic particles, they discovered that these intuitive rules no longer apply. Instead of certainty, there is probability; instead of fixed paths, there are distributions of possibilities; instead of clearly defined objects, there are entities that blur the line between particle and wave. One of the earliest breakthroughs came when scientists studying heat and radiation realized that energy is not emitted continuously but in discrete packets called quanta. This discovery shattered the classical assumption that energy could vary smoothly and led to the development of quantum theory. From that moment onward, physics began to reveal a universe that is not a rigid machine but a dynamic system governed by probabilities and interactions. At this microscopic level, particles such as electrons do not have definite positions until measured; instead, they exist in a spread-out form described mathematically by a wave function. This wave function encodes all possible outcomes, meaning that before observation, a system exists in a state of potential rather than certainty. This idea is deeply counterintuitive because it suggests that reality is not fully determined until it is observed. The implications of this are profound, as they challenge the notion of an objective universe independent of measurement. In quantum physics, observation is not passive; it plays an active role in shaping outcomes. This leads to a radical reinterpretation of what it means to exist, as objects at the quantum level do not possess definite properties until interactions occur. The shift from certainty to probability is one of the defining features of quantum physics, and it marks a fundamental departure from classical thinking, forcing us to reconsider the very nature of reality. Another central concept in quantum physics is wave-particle duality, which reveals that all entities at the quantum level exhibit both wave-like and particle-like behavior depending on how they are observed. Light, for example, was long understood as a wave due to its ability to produce interference patterns, but experiments later demonstrated that it also behaves like a stream of particles called photons. Similarly, particles such as electrons, which were traditionally thought of as tiny solid objects, can produce interference patterns characteristic of waves when passed through a double-slit apparatus. This duality is not merely a matter of perspective or measurement error; it is an intrinsic property of nature. The double-slit experiment illustrates this phenomenon in a striking way. When particles are fired through two slits without observation, they create an interference pattern as if they are waves passing through both slits simultaneously. However, when an attempt is made to observe which slit each particle passes through, the interference pattern disappears, and the particles behave like classical objects. This experiment demonstrates that the act of measurement fundamentally alters the behavior of quantum systems. It suggests that particles do not have definite paths in the absence of observation but instead exist as a superposition of all possible paths. This challenges the classical notion of a single, objective reality and introduces the idea that multiple possibilities can coexist until a measurement is made. The concept of superposition is one of the most fascinating aspects of quantum physics, as it implies that systems can exist in multiple states at once. For example, an electron can be in multiple positions simultaneously, and only when it is measured does it appear in a specific location. This behavior is not limited to theoretical constructs; it has been confirmed through countless experiments and forms the basis of emerging technologies such as quantum computing. In these systems, information is stored in quantum bits, or qubits, which can represent both 0 and 1 at the same time due to superposition, allowing for vastly more complex computations than classical bits. The dual nature of matter and the principle of superposition together reveal a universe that is far more flexible and interconnected than previously imagined, where possibilities coexist and outcomes are determined only through interaction. The probabilistic nature of quantum physics is further emphasized by the uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot both be known with arbitrary precision at the same time. This principle is not a limitation of measurement technology but a fundamental property of nature itself. The more precisely one property is known, the less precisely the other can be determined. This introduces an inherent fuzziness into the fabric of reality, where exact knowledge is impossible at the smallest scales. The uncertainty principle has profound implications for how we understand motion and causality, as it means that particles do not follow precise trajectories like classical objects. Instead, their behavior is described in terms of probabilities, with a wave function providing a distribution of likely outcomes. This probabilistic framework extends to all aspects of quantum systems, meaning that even with complete knowledge of a system's wave function, only the probabilities of different outcomes can be predicted, not the exact result of a single measurement. This marks a fundamental shift from the deterministic worldview of classical physics to a probabilistic one, where randomness is not due to ignorance but is built into the structure of reality. Another deeply intriguing phenomenon in quantum physics is entanglement, which occurs when two or more particles become linked in such a way that the state of one particle is directly correlated with the state of another, regardless of the distance between them. When entangled particles are measured, the outcome of one measurement instantly determines the outcome of the other, even if the particles are separated by vast distances. This phenomenon appears to defy the classical idea that information cannot travel faster than the speed of light, leading to what was famously described as spooky action at a distance. Despite its seemingly paradoxical nature, entanglement has been experimentally verified and is now a key resource in quantum technologies such as quantum cryptography and quantum communication. It suggests that the universe is fundamentally interconnected at a level that transcends classical notions of space and separation, where distant objects can share a unified state. The uncertainty principle and entanglement together paint a picture of a universe that is not only probabilistic but also deeply interconnected, where the behavior of one system can influence another in ways that challenge our intuitive understanding of locality and independence. As quantum physics continued to develop, it evolved into a more comprehensive framework known as quantum field theory, which describes the fundamental constituents of the universe not as isolated particles but as excitations of underlying fields that permeate all of space. In this view, every type of particle corresponds to a specific field, and what we perceive as particles are simply localized vibrations or disturbances in these fields. For example, an electron is an excitation of the electron field, while a photon is an excitation of the electromagnetic field. This perspective unifies the concepts of particles and waves, as both are understood as manifestations of field behavior. Quantum field theory provides a powerful framework for understanding the interactions between particles, including the fundamental forces of nature, and it forms the basis of the standard model of particle physics. Within this framework, forces are mediated by exchange particles, such as photons for electromagnetic interactions, and the behavior of these particles is governed by the principles of quantum mechanics.